Hi, and we're back. So now we are going to talk about the first notebook in the data science section of this tutorial, and that's going to be linear algebra. Just a quick note, the first two notebooks in this section are going to be linear algebra and statistics, and linear algebra and statistics are two of the topics that I would say data science is really just based on linear algebra and statistics. So having an understanding on both topics will hopefully be helpful when you are working on your data science project. So let's go ahead and get started with this notebook. And again, similar format, I will just load some of the packages here. And the first thing I want to say here before we get into the details is that matrices in Julia are stored in column-wise. So like in memory, it's not really a matrix. It's not a two-dimensional structure. It's really just a one-dimensional structure that's going by columns. So a matrix that is stored here in this, or a matrix that has these numbers over here, this 3 by 3 matrix, is really stored in memory as 1, 11, 100, and so on. So one right off the bat advice I would say before we get into the details is whenever you have a matrix and you want to access elements of the matrix, it is very, and you care about performance, supposedly, it is very advisable that you actually access the numbers via columns and not via rows. So if you're having a for loop that's going to go over the columns, that's going to be faster than going through the rows. All right, so that's one quick note for you to know. So let's just get started with creating a random matrix that is going to be of size 10 by 10. And then the next thing we will do on that matrix is that transpose the matrix. So have the rows become columns and the columns become rows. I'm actually going to create a matrix that is going to be symmetric, positive, definite. And A here, I'm just going to use A times A transpose to actually visualize what a matrix multiplication is going to look like. And okay, so let me actually cut this line here and just rerun this again. And quick things I will execute here. So is positive definite of A. Hopefully that's true. Yeah, that is true. And so not any matrix that you take it and its transpose is going to be positive definite, just in case you don't have that linear algebra background. But here, just because it's a random matrix, it is going to be most likely a positive definite matrix. So let's go. The next thing I had here is, sorry, that didn't, I think I had a line here that I wanted to cut exactly. Okay, so that ran. And then the one thing I wanted to show you here is you can actually access elements in a matrix via two indices, so row, column. So here is row 1, column 2. But also, since this is a 10 by 10 matrix, and I just described to you that matrices are really stored in a linear index by columns, so the 11th number is really just the first row, second column entry. And that should turn out to be true. That's really just because a matrix is stored as a linear dimensional in memory. All right, so quick things you would need from a linear algebra routine are solving a system of linear equations. That's the most common things you would want to do in linear algebra, solving this equation of ax is equal to b. So here, the first thing we're going to do is create another random, vector in this case. That's going to be rand of 10. We'll talk about the difference of a matrix and vector in just a second. And then the next thing we will do is solve a system of linear equations, ax is equal to b, by calling this backslash operator. You would probably never want to use the inverse function. Backslash is actually a very powerful tool that will solve your linear system way more efficiently than using the inverse of a matrix. So as a rule of thumb, if you have a system of linear equations, call A backslash B. And now just I want to show the norm of ax minus b. That should be a really small number. So this was almost machine precision, and basically ax is equal to b in this case. So let's actually look at the types here. So A is of type array float comma 2, float 64 comma 2. So we've seen something like that before in the data file, but the data file had some like integers with strings and so on. Here, what we have is array of float comma 2. What that means is that this array is two-dimensional, so it's a matrix, and the types of the elements in that matrix are of type float 64. So that's what this means. The type of B is again an array, but the dimension is 1. So one thing to note here is that there is a distinction in Julia between a vector and a matrix. So a vector is a one-dimensional array, and a matrix is a two-dimensional array. And again, that's similar format. The type of every element in B is a float 64. So, and then type of rand 1 by 10, you will see that even though this is really a one-dimensional kind of vector, if you want to think about it, because it's 1 by 10, but really it's two-dimensional. So the way Julia thinks of dimension is if you're in the same column, you're fine. You're one-dimensional. Once you move on to multiple columns, you're now in the two-dimensional case. So here, since it is of type of 1 by 10, so you have multiple columns, you're back to the two-dimensional case. One quick thing, because this could be tricky sometimes, if you actually do rand of 10 comma 1, this is going to be two-dimensional in terms of the type, if you're actually looking at the type. That's because you've actually declared a dimension here, which is, even though it's 1, that's still going to be treated as a matrix format. So sometimes you will see some functions only take matrices, and if you want a quick way to convert your vector to a matrix type, that's a hacky way to do it. But if you actually have a vector, you should only use rand of 10 or just like a one-dimensional vector. Okay, so and lastly, transpose of A, the type of that thing is actually an adjoint. A quick note about adjoint here is that in Julia you don't, it's called the lazy adjoint. And what that means is that sometimes when, for instance, you're doing A times A transpose here, you don't necessarily need to transpose the matrix itself to come up with every entry in the matrix A. So the matrix A, every element in it is a dot product essentially between a row vector in the first matrix and a column vector in the second matrix. Now, when you're doing A times A transpose, and you already know that A transpose is of type adjoint, well, you can take the row index, so element aij is going to be element dot product between row I and column j in the A transpose, but it's also the dot product between row I and row j in the A itself. So column j in A transpose is row j in A, right? So by not actually materializing what A transpose is, like sometimes you don't actually need A transpose. All you need is to perform an operation on A transpose. And using this adjoint idea or lazy transpose is actually very helpful in this case. Okay, so moving on, just to make sure that you know these terminologies, these are synonymous. So array of dimension 2 is really a matrix, array of dimension 1 is really a vector, A transpose is an adjoint type. All right, so we've covered adjoint mostly. I just want to say, like, if you have an adjoint type, you can always go back to the parent of adjoint, so what actually the A itself was. So that was the actual matrix. The A itself is going to be, so the size of function is going to give you how many bytes, I think. Yeah, how many bytes the vector or the entry you're passing, the variable you're passing it to. So size of, size in bytes of a file or a value or an object. All right, so size of A is 800, and that's because every element is 8 bytes, and then you have essentially 10 by 10, so 100 numbers, so 8 times 100 is going to be 800. If you actually want the matrix A transpose, you really want to work with it itself. One way to do it is to do copy of A transpose, but most likely in most cases you probably don't really need it, but just so that you know. Okay, so the backslash operator is, again, I'm gonna get the documentation about it here. Really, it's just solving a system of linear equations. One thing I want to say here is that, yeah, here for a rectangular A, the result is the minimum norm least square. So what's cool about A backslash B or A backslash, yeah, A backslash B is that it's solving least square problem if the problem is not solvable. So what that means is that if there's no such x where you can solve ax is equal to b, what backslash is going to do is going to find an x such that the norm of ax minus b is minimized, and that's a least square problem. So the two norm, yeah. So that's one interesting thing to know about it here. And yeah. And again, it will actually, the reason I said you don't really need to use the inverse if you're solving this problem is because backslash is actually pretty smart. So what it does is that it tries to find a proper factorization of the matrix. If A is upper triangular, like it's gonna do no factorization. There's a really easy way to solve an upper or lower triangular matrix backslash B, or like if you have a diagonal matrix, it's super easy, you just divide by diagonal entries. So there are ways where if a matrix has a certain type, it's really easy to solve the problem. So think of it as like it kind of goes through a flow chart of like, is this matrix so and so? If it is, then I'll just use this. If it's not, then I'll use this other thing. So it's pretty smart in detecting what way to solve the problem. All right, so factorization. So we've already saw something called an LU factorization somewhere here, but we glossed over it. So let's actually look at what these things are going to look like. So in linear algebra, if you haven't had like a strong background in it, very simply, there's a lot of factorizations on matrices that we often use to most of the time like solve a lot of systems of linear equations. So if you have the factorizations, it becomes easier to solve these systems. And sometimes we could use them for other reasons, like a QR. I think in computer vision, they use the QR factorization for some sort of, I forgot the details, but I remember it from one of my courses, something like camera calibration and stuff like that. So these factorizations do come up in a lot of fields. So let's see how you can do factorizations in Julia. The first factorization we'll go over is the LU factorization, so lower upper triangular. P here is really just a permutation matrix on A. So we will see that LUA, so if you want to access the elements in the LU factorizations, you're going to get the L factor, the U factor, and the P factor, and LU minus P times A is going to be very small. The norm is essentially 0. QR factorization, very similar pattern. You call the QR function on A. And let me say just one quick thing. All these functions are coming from the linear algebra package. So linear algebra and sparse arrays are really what you would probably want to use if you're doing a lot of linear algebra and sparse matrix computations in Julia. All right, so moving on, yeah, so LU factorization, QR factorization, and the norm is essentially the same. I'm just checking here that A is positive definite, just because the Cholesky factorization requires that A is positive definite. That's a type of factorization where the U factor and the L factor is kind of like an LU factor, except that the L and U are the transposes of each other. So let's see what this is going to look like. Yeah, so Cholesky of L times Cholesky of A, Cholesky L, the lower triangular matrix times U is equal to A. Let me actually just show you Cholesky A dot L, and then let me show you Cholesky A dot U. And yeah, you will see that these are really the transposes, so 2.15, 1.73, so the first column here is really the first row there. So that's just a special type of factorizations that only works on positive definite matrices. So another quick thing is factorize of A is this function where it just returns the meaningful factorization on a specific matrix. So since A here is positive definite, it makes sense. Like one of the common factorizations you would want to use here, or like one of the most powerful factorization on that specific matrix is going to be the Cholesky factorization, because that's pretty cool. Like L and U are actually the transposes of each other, and these are the low rank factors. So it just picks the right factorize is really just picks the convenient factorization is probably the right word here. So yeah, again, if it's positive definite, it's going to give Cholesky, and given a specific type, it's going to give the specific factorization. So if you don't know which factorization to use, one quick way to do it is to run the factorize function. Yeah, there's other types in Julia. So as you saw here, there's like, if it's diagonal, if it's tridiagonal, if it's symmetric, real, like these are types of matrices. These could be actually specified when you form your matrix. So like, you can form a diagonal matrix, and when you form, let's say, yeah, so here is an example of forming a diagonal matrix. So you can form a diagonal matrix by, actually, oh no, diag-M is what I actually wanted. Yeah, you can solve a diagonal matrix, diag-M, like that. So yeah. So now you know it's a diagonal matrix. If you want to run I is a function. So you can run I of 3, which is going to be just a diagonal matrix of 3 elements here. What I'm curious about is if I run this. Yeah, it's an array. So that's interesting. But if I actually do convert of diagonal int 64,2, is that gonna work? It's not gonna work. I is oh, I see. Okay, so here what I want to do is array of int 64,1. That's still not going to work. Well, one easy way to do it is really if you actually do diagonal of, I think this should work. Perfect. Okay. Well, yeah. So diag-M actually, interestingly, it doesn't return a type of diagonal matrix. But if you do diagonal of that vector, you can get a diagonal matrix. All right. So yeah, we've already covered I. It's just a diagonal matrix of all the entries equal to 1. If I have an A, so I have an A here, right? And I want to quickly add an I to it. I don't really need to worry about dimensions. I can just call the function I, and it's going to figure out what values of I want. So like 10I, that's just going to work fine. All right, so moving on to the linear algebra, sparse linear algebra part. Here, mostly we're going to be using the sparse arrays package, which we've already declared above. Here, we're creating just a sparse random matrix of size 5 by 5 with some probability of what is the probability of value is going to be non-zero. And if it is not zero, it's just going to create a random number there. The way to access, so S is, if you're familiar with one way to store sparse matrices, you obviously don't store the entire matrix of zeros and non-zeros because there's usually very few non-zeros. You use a compressed form to store them. One of the common forms is compressed sparse column, which allows you to basically just get access to the numbers pretty quickly by just declaring three vectors that will define the matrix. So we'll take a look what these vectors look like. So here when I declared matrix of S, what I did here is that I actually made the matrix dense. So when I made the matrix dense, I can actually look at the numbers and convince you what S.rowval and S.column pointer is going to look like. So the column pointer here is saying, well, I have, first of all, 5 columns. And the first column is starting at the entry 1 in this row value. And the entry 1 is actually the third row. And column 1 is starting here. but the first value here is 3, which means element 3 in the first column is non-zero. And then the second column is starting at index number 2. So this is the second column starting here. It's saying, well, the first element in that column is non-zero. It's also saying the second element in that value is non-zero because column 3 does not start until 5. So 1, 2, 3, 4, 5. This is where the third column is going to start. So 1, 2, and 5. 1, 2, and 5. That's correct. And so on and so forth. So these are really just the indices of where a column starts. And if you say, well, I want to look at where column 1 starts, you can just go here and look at everything up until where column 2 starts. You can get that index by just subtracting 1 from this. And then the values themselves are, actually, let me keep this as it is and do s dot nz val. Ooh. These are the actual values. You're going to see that they are vectorized here. So this is the first element here, 0.107, and so on and so forth. So this is how really a sparse matrix is stored. Like all you need is really just these 3 vectors. You also have the dimension as the size of the matrix. So I think it's S of n and m. So rows are m and n is columns. So you have all the information you need about the matrix just without the zeros. And that's just a more compact way to store the sparse matrix. All right, so moving on to just getting more data sciencey here in the linear algebra section, I am going to work here with some images. So one way to think about images is to think about them as matrices. Every pixel in an image is a number, and you can think of these numbers as basically forming the matrix itself. So here I'm going to load an image that I have here in the in the directory. And the reason I'm working with this image is because if you look at it, there's like a lot of detail in it, and we'll see what we're going to do with this image in just a second. So quick idea of what the type is about. So the type of X here is still, it's an array actually, 2-dimensional array, but except that the values in each of these, instead of like the float 64 example we saw earlier, now it's actually an RGB value. So if I actually access the first element x1 of 1, what is that? It's actually an RGB value. That's the value. And if you actually look at the top very tiny 1 entry here, this color looks pretty much like this color, right? Okay, so one way to work with figures when you have RGB values is just to transform them to grayscale, and that way you just have one number to deal with. Just before we move on with the RGB, with the grayscale image, there are pretty easy ways to get the R, G, and B layers out of this figure, and that's how you would do it. Let me just actually declare. Yeah, so this is the Z image. Sorry, the blue layer of this image. What I'm creating here is, so first of all, Z here is just a matrix of all zeros. So what I'm doing with creating this image is I'm passing a matrix of red values to be 0, passing a matrix of green values to be 0, and then passing, RG, and then B, we're passing a matrix that is actually the blue values that I've computed here out of the image x1. So that's how I got the B value. If I'm doing RGB, I'm just going to get the green scale version. All right, so moving on to the gray scale. Sorry, here was the green scale. This is the grayscale. So going back to the grayscale, one quick way to transform this grayscale, which is an image, the type of it is still an image, or array of grayscale values, is just to call the float 64 on that image x gray. So now it's just going to transform each of these numbers, which was the grayscale value, is going to become like an actual number. So one way to downsample a figure in general is if you want to use the SVD decomposition. So SVD is a very, I would say out of all the factorizations, SVD is probably the most I think it's the most interesting to me, at least, because it does have it does give you so much information about your data. First of all, it's an indication of how high dimensional your data is. So a lot of times the SVD could tell you, say, like if you have sorry, not high dimensional, just like the rank of the matrix. So like if you have just one singular value that is non-zero, you could immediately know, oh, like this is really just a low rank, very low rank matrix, then I can store it in much less memory on my computer. And another way is this very famous theorem about the SVD, the Eckhart-Young theorem, which says if you want to kind of get a low rank estimation of your matrix, the easiest way, or not the easiest way, actually, the closest way you could do it approximately is by taking the top singular values out of these matrices. So without like throwing at you so much jargon, let's just work with the SVD and see what happens when we extract the top singular vectors and singular values. What's going to happen? So if I just call the SVD here, there's really three components that you want to look for. The first one is the U factor. The second one is the S factor, and the third one is the V factor. So these are the singular values. So what I will do next is, so first of all, let me just tell you that if I call SVD, let me copy this. I don't know why I gave it this name. It's kind of a weird name. U times diag m of what am I using here? SVD underscore v dot s. So that's the vector of diagonal values times SVD underscore v this time. U sigma v transpose. Let's get the norm of that minus the actual matrix we started out with. Oh yeah, that is dot v. Ah, man. All right, perfect. Okay, so this is how we get the norm, and we see that this is the decomposition of this matrix. Okay, so what we will do next is we will actually start extracting each three things together. So first column of U, first column of V, and then the SVD S value, which is a scalar, going to be here as a number, and multiply U times V transpose. So this is a rank 1 matrix, this is a rank 1 matrix, and so on. And we're adding all of these together. So we're taking the top four singular values, singular vectors, and appending them, all of them together, and forming them in this image 1 file, or image 1 data matrix. And then I'm going to call the gray dot on it. And what you will see is something, like if you can see, this is, obviously you can't see anything specifically in it, but you can see something resembling what we already had here, right? You could see there's these patterns in the top of the ceiling. And if I actually just use the top singular value alone, it's going to be a little less obvious, right? Like this is not great. When I add just the second one, it's going to get better. And if I add the third and fourth one, it's going to get even better. So what I'm saying is the more I'm adding some of these top singular values, the better it's getting. So what happens when I actually use the top 100? Let's see. It's almost identical to what we already had in the beginning. So what this is doing is that we just downsampled this image by storing less information. So here I'm using only 100 columns versus when what this matrix really is 283 columns. So we're using way less columns to do the same thing. Let's see, actually, just out of curiosity, what happens if I only use the top 50? Yeah, top 50 is pretty good. Like if you're looking at it, you can see some like weird things going on here. Maybe 100 is a pretty fair number for this. All right, so that was one quick example of how you could use SVD. The norm here, is not going to be almost 0, right? Like we didn't actually have the exact same decomposition, except that visually as an image, it looks almost identical, right? But the actual norm, there's some values that do not exist. So from an image perspective, you've done the downsampling, you're using less numbers, but by using less numbers, you're actually losing some precision, and this is the norm difference between the two images. The next example we're going to cover is face recognition, and this is a very straightforward, simple problem from face recognition. I do have to say that it could be, or it most likely is, more complicated in real scenarios. But here what we have is that some data set where we have just a lot of images, square images of, sorry, they're not square actually, rectangular images of faces of people. And if I actually, this data set is the Yale data set, extended Yale data set, and it's readily available online. So if we do call the first image, we get the V vector, which actually, this is a dictionary, we've seen something similar before. We're calling the first column of that, and we're reshaping it into 192 by 168, which is the dimensions of these images. So each of these images is given to us as a vector, and now we're reshaping them and putting them as a 192 by 168 to look at the grayscale version of those images. All right, so now the question is, what if I have a query figure or image B here, and I'm trying to detect where in my dictionary, where in my set of images do I find this query image? What's the closest image to it? The problem translates into forming, so first of all, I'm going to create a query image here by calling this Q. So I've already called the first image Q. I'm just reshaping it to just a column, and now it's, again, it's not in grayscale, so it's not an image, it's just a vector of numbers. And this is just, this number is really 192 by 168. And then I'm just going to take the same data set, except that I'm just going to skip the first one. So the first element that we're looking for is not in the data set anymore. Now I do have to mention that here, what we have is that every person has more than one image in the data. So it's a different image, but it's the same person. But we would expect that the person we're looking for will still have images in that data set, and hopefully we will be able to find them. So one way to solve this problem is now we have the matrix A, where we've stored the second column all throughout the end, like for all subjects we have. And the next thing we want to solve here really is AX is equal to B. We want to find this X, which is a representation of a combination of columns in the dictionary matrix A, where it is going to be equal to B. And now once I found A, actually the image, once I found X, the image I've actually found is the image A times X. So X is really just a combination of whichever vectors I'm interested in looking at. And once I found them, again, this is a vector, not a matrix, so I'm reshaping it to a matrix to look at the grayscale image. And if I look at these two images, they're almost identical. And the norm is almost essentially 0. Now, finally, what I'm going to show here is just make the problem a little harder. So instead of Q as I used it earlier, I'm just going to add random noise to it. I'm just going to renormalize back to have numbers between 0 and 1 and be able to see them as grayscale images. So I've added noise, and then this image is kind of blurred out. And now I'm just going to do the same exact thing. And now solving this problem is probably going to give me a higher norm, but we will see that in just a second. Yeah, so again, the same thing is we're doing the same thing here. A is really the dictionary. Yeah, it is a different norm. But if I actually, again, look at the image itself, it's pretty similar, or I would say we were able to detect the person, even though this is not exactly the image we found, or like this and this were so much closer, but we were able to find a pretty close image to the person we're looking at, and that's the person, or the image A times X. And finally, I hope you can check all these boxes after finishing this notebook. And the cool finding is that now if we have an image of someone and we have a dictionary of images, We can solve for the problem via the ax is equal to b problem, and we can make use of the backslash operator, which is pretty powerful because it could solve for a least square, not necessarily just ax is equal to b. It will minimize the norm. So here, as you saw, ax is equal to b was not actually 0, so it just minimized the norm. And yeah, next time you have an image in a dictionary, you can actually look for the person in the dictionary. And that's about it. We'll meet in the next notebook. Thank you.